Heat transfer example problem, internal flow with constant external fluid temperature. Forced cold air induction is used for internal combustion engines to improve engine power output by delivering colder, denser air to the fuel injector, thus more air-fuel mixture to the cylinders for each power stroke. Cold air at an inlet temperature of 20 degrees Celsius at a mass flow rate of 0.05 kilograms per second enters a rectangular duct that is 5 centimeters by 10 centimeters and 1 meter long and flows through a hot engine compartment at 120 degrees Celsius at a velocity of 20 miles per hour. For Part A, estimate air temperature at the duct exit. For Part B, estimate the average duct temperature. For Part C, estimate duct temperature at the exit. Our first assumption for this problem is steady flow of air through the duct and outside the duct in the engine compartment. Our second assumption is constant properties for the air inside the duct at the mean fluid temperature and outside the duct at the film temperature, which will be defined later. Our third assumption is that there is negligible radiation for the interior and exterior boundaries. This is a reasonable assumption for moderate temperatures combined with significant convection at the boundaries. Our fourth assumption is that we can obtain reasonably accurate convection coefficients using ideal Nusselt number correlations for this complicated geometry. Our fifth assumption is that the air is an ideal gas at atmospheric pressure, which will be used to look up properties. Clearly, these are some significant assumptions, and we should only expect an accuracy of about plus or minus 20% for our results. For Part A, to calculate the mean outlet temperature for the air in the duct, we use the equation obtained from a one-dimensional analysis of the flow in the pipe with a constant external fluid temperature. Solving for the mean outlet temperature, we get the result shown where the thermal resistance is due to the resistance to convection from the air inside the duct to the air outside the duct in the engine compartment. Note that we are neglecting the resistance due to conduction for a thin-walled duct. In order to solve for this temperature, we need to estimate the convection coefficient for the air inside and outside the duct using Nusselt number correlations. First, for internal flow in the duct, we begin by calculating the Reynolds number to determine the flow regime. Note that we need to evaluate the properties at the mean temperature in the duct, which requires an iterative calculation. For these calculations, I used ease to automate this process, resulting in a mean temperature of 298.5 Kelvin based on simple averaging of the inlet and outlet temperatures. Also, since this is a non-circular duct, we need to calculate the hydraulic diameter, for which we get a value of 6.67 centimeters. Note that this corresponds to a pipe length of 15 diameters. Finally, we get a Reynolds number of 36,000. Recall that for internal pipe flow, if the Reynolds number, based on diameter as the length scale, is greater than 2300, we assume the flow is turbulent. Based on this, we select a suitable correlation for the airflow that is commonly referred to as the Dietz-Beutler correlation. Substituting in values, we get a Nusselt number of about 90 and a convection coefficient of 34 watts per meter squared Kelvin. Second, for the external flow outside the duct, we again begin by calculating the Reynolds number to determine the flow regime. Note that we now need to evaluate the properties at the film temperature, which is defined as shown, and is determined to be 372 Kelvin using an iterative technique in ease. Based on the hydraulic diameter and external flow velocity, the Reynolds number is about 26,000. When we look in our textbook for a correlation for flow over a rectangular duct, we find that there are none. The best approximations available are for cross-flow over a cylinder or square duct, where coefficients for our Reynolds number range are given in the table. Using these correlations, we get a convection coefficient approximating the duct as a cylinder of 42 watts per meter squared Kelvin. Alternatively, if we calculate the convection coefficient for a square with sides of length A and B, we get that this value ranges from 35 to 44 watts per meter squared Kelvin. Thus, we conclude that using the first calculation will be a reasonable approximation for this case. Furthermore, note that further calculations using this range of values would be useful for determining how sensitive our results are to this parameter. Finally, substituting in values to our earlier equations, we get a total thermal resistance of 0.175 Celsius degrees per watt and an outlet mean fluid temperature of 31 degrees Celsius. This result is only 10 degrees higher than the inlet temperature and much lower than the engine compartment, which is at 120 degrees Celsius. Thus, even without insulation, the duct will serve its purpose of delivering cold air to the engine. Of course, if you want to keep the air in the duct even cooler, insulation would help to do so. For Part B, to calculate the average surface temperature for the duct, we begin by making some preliminary temperature difference calculations for the inlet and outlet flow. Then, we combine these to calculate the log mean temperature difference. Recall that this temperature difference represents the average temperature difference between two flows that takes into account the exponential variation in the mean fluid and surface temperatures. Next, using the resistance network introduced in Part A, we calculate the total heat transfer to be 540 watts, the mean air temperature in the duct to be 25 degrees Celsius, and the mean surface temperature to be 78 degrees Celsius. This is about halfway between the internal flow and external flow temperatures, which makes sense because we found that the convection coefficients have a similar magnitude. For Part C, to calculate the duct temperature at the exit, we do a surface energy balance on the duct at the exit. Based on this, we get that the temperature is a weighted average of the surrounding temperatures, where the convection coefficients are used for the coefficients. This results in a surface temperature of 80.2 degrees Celsius, which is a little higher than the mean surface temperature, as expected. Finally, before ending, we note that a better model for calculating the mean fluid temperature would be to integrate the mean temperature over the length of the duct. Substituting in our mean temperature distribution that varies with axial location, we can integrate to get the result shown. Substituting in values, we find that the mean temperature calculated using this model is less than 1% different from the value obtained from simple averaging. Thus, it is not necessary for this case to use this more complicated calculation. Furthermore, if we repeat this type of modeling approach for the mean surface temperature, we also get a value that is within 1% of the value obtained from the overall resistance network model. Thus, once again, it is not necessary for this case to use this more complicated calculation, particularly given the level of uncertainty in the Nusselt number correlations being used to approximate the convection coefficient.